Hello, Nashville. Sounds like the mic's working. There are a lot of people here standing in line because this conference has become the place that major milestones in Bitcoin are announced, and everyone is standing in line for Trump and maybe Elon Musk to make an announcement which is going to be yet another milestone in Bitcoin. But that isn't the only significant milestone that has been at this particular Bitcoin conference. Just a few days ago, BitcoinOS announced something that on a technological level is certainly no less profound. For the first time ever, zero-knowledge proofs were introduced as transactions to Bitcoin Mainnet. No soft fork, no changes. We actually have liftoff. For the first time ever, we have ZK proofs on Bitcoin. And what does this mean? It means that Bitcoin is now able, even without Lightning Network, to scale to thousands of transactions per second. It means that Bitcoin can now have native private transactions. And it means that you can now, for the first time, introduce sophisticated smart contracts into Bitcoin. But perhaps the most phenomenal thing that this does is it allows Bitcoin to have truly trustless layer 2s, roll-ups, where any type of functionality can occur. It used to be the case that people said they needed to create new chains because Bitcoin was old, boomer coin, and you couldn't do enough things on it. But with zero-knowledge proofs, Bitcoin now has the power to do anything that Ethereum, that Solana, or any other piece of software in the blockchain space can do. So a lot of people have been asking questions, how was this accomplished? How did BitcoinOS manage to do what people had said was impossible? To introduce zero-knowledge proofs without a soft fork, without a new BIP, without any new opcodes. And here, from BitcoinOS, for the first time on stage, is Gadi Guy, the CTO of BitcoinOS, who's going to explain how his team managed to pull off the impossible. Gadi.
Hi guys, so I'm Gadi. I want to tell you today about something that I personally find very, very exciting, which is that we have successfully verified the ZK proof on top of Bitcoin, keeping the existing consensus rules. And I want to tell you a little bit about how we did it and about the opportunities that that opens up for the Bitcoin ecosystem. Okay, so as you might have heard, on July 23rd, we have done something for the first time. We have verified the ZK proof on top of Bitcoin. And I want to tell you how we did it. So a ZK proof verification is essentially a program that's very, very large. And it's not really practical to run that on top of Bitcoin because Bitcoin script is extremely limited and doesn't have the ability to do any kind of advanced math. And so a snark verification program, if you did write that in Bitcoin script, would probably be about at least a terabyte in size, which is completely science fiction. There's no way to run that on Bitcoin. And so what we did was we turned that into an interactive protocol that allows two or more parties to narrow down the program and negotiate the smallest possible chunk of that program that we can actually turn into a Bitcoin script code. And we built a very, very large taproot tree that includes all of these little chunks. And so after the protocol, after these two parties narrowed down the program to the bit where they disagree on, only that bit can be run as a taproot leaf. And in the end, you get a proof that runs on top of Bitcoin and either succeeds if the snark verification succeeds or fails if the snark verification fails. So to do that, we've built a very, very large taproot tree. We invented a new kind of virtual machine for this purpose that is specifically optimized for the kind of math that elliptic curve cryptography requires. And we used that, we ported the snark verification code to that virtual machine. And that allowed us to optimize the shit out of it. And we We also thought about doing, representing the Merkle proofs, representing the state commitment as Merkle proofs in order to keep each transaction down to at most 100K. So here you can see what a verification actually looks like. This is a real thing from Mainnet. So you have a prover and a verifier that the prover initially posts the proof to Bitcoin, and then the verifier can see this, check the proof, and decide if the proof is correct or incorrect. If the proof is incorrect, the verifier has to stake some funds in order to challenge the proof, and then they begin the interactive protocol that you see. The prover part that we call Patrick is color-coded blue, and the verifier part that we call Victor is color-coded orange. This case of the protocol took about 25 steps, which we managed to get into as few as 6 blocks.
Okay.
And the final step of the protocol that you can see here, labeled step 26, is performed by the prover. And in this case, since the proof is correct, the final transaction is successful. The idea behind this is that since this can be quite costly to do, if the prover is correct and the proof is right, then the prover takes the stake from the verifier. And if the verifier is correct and the proof is wrong, then the verifier takes a stake from the prover, which means basically that the dishonest party is the one paying all of the fees, which is good. And that means we don't really care how expensive it is. The only real constraint that we have is that we want all of the transactions to be small enough that we can make sure they get mined quickly. That's the constraint that we had in this case. So this is the initial transaction is on block 853260, and you can copy the transaction ID if you want, and we also put on GitHub a little bit of code that you guys can clone and use it to verify that the proof that we have on Mainnet is actually correct. I want to show you the code for a second, because it's really very simple. Can you read this? Yeah. Yeah. So basically, you can download the code and you can just take the transaction payload from the actual transaction on a block explorer, copy that into this repository, and then you can just the code, as you see, is coded as a jest test. You can use jest to run it, and it uses snark.js to verify the proof. Very simple, so that you can actually see that what we put on Mainnet is real. And this is the final transaction is on block 8532626. We have also attached an ordinal to that block just to make it more fun and more interesting. And that ordinal will later be used to spawn new ones. And if you want, you can join our group and get free ordinals, which is always fun. Okay, so what are the next steps? So this was a very nice and interesting demonstration, and but in order to make it a real-world application, we still have to do a few things. For example, we have to turn the two-party protocol into a multi-party protocol so that the security is real-world security. And we're going to build real-world applications with this technology. Some that come to mind is something that we call Grail, which is the first trustless or nearly trustless bridge between Bitcoin and EVMs. And what I mean by trustless is that unlike most bridges today that rely on a multi-sig, our bridge will not rely on a multi-sig. So it enjoys the full security that ZK proofs can provide. Additional killer apps that we can build on this technology are ZK rollups, smart contracts, decentralized exchanges, stable coins, all of these great and wonderful things that exist in the EVM world and don't exist yet on Bitcoin. And that's something that we think really should change. Please scan the QR code. We're hiring coders. If anybody is interested in helping us, you can join our Telegram group, and if you're a top-notch coder, we'll welcome you to our team. And that's it. Time's up. Thank you.